Welcome back. All right. So now let's look at how does this blood transport oxygen. So we know that the blood will transport O2 and deliver, transport CO2 and deliver. So basically it's right here. You pick up, transport, deliver, right? So you need to be able to carry it. The thing is that how does the oxygen know that it's time to go into the blood? Or how does the oxygen know that it's time to leave the blood? How does oxygen know? And how does the CO2 know it's time to go into the blood and it's time to leave the blood? So they don't know, right? How do they know? They are not smarter than you. If you don't know, how do they know, right? So they don't have brain to like decide, okay, it's time to get up, it's time to get off, right? They don't. So the thing to make them get on or get off is the pressure. So if the environment has good oxygen pressure, it will push oxygen on. And in the lung, you have good oxygen pressure because in the air, 20% of those air are oxygen. So you have abundant oxygen. They will push it up. I think it's recording, right? I hope. Yes. They will push it up. Well, if it's in the tissue, organ, the environment over here doesn't really have too much oxygen because oxygens are all used by the local tissue. So local tissue use those oxygen. So this is oxygen rare um, uh, environment. Yeah, so you don't have a lot of oxygen here. And with that one, the no oxygen pressure, oxygen will leave. So basically it's that. Now let's look at the CO2. In the air, CO2 amount is very low. You know, CO2 is like 0.00 something, 0.3 something percent, very low. Yeah, in the air. Even though we all breathe out CO2, but CO2, you know, very low. So with that low CO2, you don't have huge pressure to push on CO2. So CO2 leave. But in the local tissue, it's very different. It's acidic. It's environment, not acidic, but environment will easily become acidic. Environment produce a lot of CO2. So that pressure, the CO2 pressure will push the CO2 get on the blood. So it's all pressure. So it's physics. It's not, you know, something that they know that to get on, or they know it's time to get off. It's not. So it's all physics. They all push it. Either in the air, push the oxygen to the blood, or in the local tissue, that low oxygen environment, oxygen get released. And same thing applies to the CO2. In the local tissue, high CO2 pressure to push the CO2 get into the blood, while in the air, in the alveoli, the air doesn't really have too much CO2, so CO2 get released. All right, so that's that. That's everything. All right, let's see. So let's look at the more molecular detail. So here is the oxygen transport. So oxygen transport is by what? It's by red blood cells. And how does red blood cell carry oxygen? Is hemoglobin. So in a red blood cell, we showed this picture earlier. In the red blood cell, it has this is the red blood cell, it has the hemoglobin. Each hemoglobin has 4 chains. So each chain can carry 1 oxygen. So when pressure is high, they'll bind on it. If the pressure is low, they will leave. So let's look at these scenario in the lung and in the local tissue. So, okay, so here is that we can measure this saturation. This is a saturation percentage, and we can measure it as a pulse oximeter. And so you can usually get 2 numbers. One is the pulse, the heart rate. The oximeter is the oxygen saturation percentage. So you can get 2 numbers. One is oxygen saturation percentage, which is usually around 95 and higher, our blood are very good at transport carrying oxygen, and then the pulse is right here. So that's that. We talk about this saturation percentage, just an overview that this is how we determine, how we present the oxygen gets onto the hemoglobin or leave the hemoglobin. And that and as I described earlier, that the primary factor to determine whether oxygen to get on the blood or leave the blood is pressure. So here we can see the x-axis is oxygen partial pressure. In the air is about 150 mmHg. So you have 100% saturation, which is what you see in the lung. But in the local tissue, the environment doesn't really have that strong oxygen pressure. So without that pressure, oxygen leave the hemoglobin. So hemoglobin can carry only 50% to 75%-ish of this oxygen in the hemoglobin. Yeah. So this is curve is called oxygen dissociation curve. So that's that. And so this one, let's take a look at when it's in the lung. Here is if we draw a line, if I may draw a line. I hope this will work like that. All right. So this corner is the lung. This corner is in the tissue. So in the lung, we have the high oxygen partial pressure. So oxygen coming into the alveoli, we breathe in, oxygen go to the alveoli. Then oxygen diffuse, and when they diffuse into the blood, they will bind by hemoglobin going to the red blood cell. So this is a red blood cell. Oxygen diffused into the red blood cell. They bind on hemoglobin. 98% of the oxygen transport in the blood are transported by hemoglobin. When this blood go into the local tissue, in the environment, here is the tissue, cell use the oxygen. So in the environment, oxygen level is very low. So this, with that low push, oxygen cannot keep on staying with the hemoglobin anymore. So they will leave. And when they leave, they diffuse out. They diffuse from high concentration to low concentration. So here is from the air is high concentration to the tissue, to the blood, which is lower concentration. But from here is this carry the oxygen from high concentration to low concentration. Then cell will use the oxygen to conduct the cellular respiration. We talked about this earlier. If you don't remember, it's right here, cellular respiration right here. So these basically describe that mitochondria use CO2, use O2 to conduct oxygen phosphorylation in order to produce ATP. So that's it. So that's the O2. All right. Now the next one is CO2. Here is the CO2. So CO2 is that we push it in the local tissue, in the local environment. We have a good amount of CO2. You know, when we produce ATP, you also produce CO2. So that is so large, and so it's like trash, right? You accumulate so many trash, and so that trash like pressure will push those trash into that river, right? And then that river will carry that trash into CO2, basically, into our air. In the air, there's no trash. There is so clean, no CO2, or very little CO2. And so that will get evaporated, not evaporated, but released into the air. So this is the situation. Then the question is, how do we transport it from the local tissue to the lung? The reason that it could be an issue is that CO2 is gases, right? So gas cannot dissolve in the fluid. Now this is fluid. Gas cannot get dissolved. It's not something that you can mixing in the blood and then get here and then release, right? O2 is different. O2, it binds on hemoglobin. So even though O2 doesn't get dissolved in the blood, hemoglobin hold on to it, transport it. But how about CO2? Which, how do we even carry it in the blood? Because it's a gases, it's a gas, right? So how do we carry it in the fluid? So the reason that the method that our body can carry CO2 is to convert that CO2 into bicarbonate. Let me show you here. So right here, CO2 transport is to convert CO2 right here. Let me see this. So when the oxygen diffuse, when they diffuse to our blood, they enter into the red blood cell, and then in the red blood cell there is an enzyme, so it's called carbonic anhydrase. In that, so here let me let me let me do something very quickly. So that is this. I think it's good. So that is that. So here, this circle indicate this is a red blood cell. How about that? So that's a red blood cell. Yeah. So when these CO2 go into the red blood cell, how about that? I think this is probably even better. Yeah. So it's here red blood cell. Yes. So when CO2 go into the red blood cell has an enzyme called carbonic anhydrase. Then it will catalyze or facilitate these chemical reaction. CO2 and water will become H2CO3. Now, actually, whole thing is in the red blood cell here. In H2CO3, and very quickly, because this is not very stable, in order to dissolve this in the fluid, these will get dissociated to become a bicarbonate HCO3 minus and hydrogen. So that's that. So how do we even get transport the CO2? We don't transport CO2. We have an enzyme to convert that CO2 to become something that we can transport. We convert it into a solvable. We can dissolve it into the fluid. We convert them into an acid, basically, carbonic acid, and this acid can dissociate to become an hydrogen. This is acidic component as well as HCO3 minus. So that's that. That's how we transport. So in order to transport CO2, majority of this CO2 is converted into bicarbonate. And with this, you can dissolve a lot. It's just like a molecule that you can, or like salt, right? You can dissolve in the water. And so you can transport a lot. And this also gives you the idea that CO2, when they enter into our water or our body fluid, they will make our environment or our tissue to be acidic. Yeah, and by detecting this acidic level, we know that our body's CO2 level is getting higher. Yeah, so that's that. All right, so that's it. So that's how we transport. So let's look at it in the local tissue. So here is that local tissue. Let me draw a line again. All right. So here is that in the local tissue. Here is the local tissue. Tissue produce CO2 because of the cellular respiration, produce ATP and CO2 and water. Now this CO2 will get diffused out because here you have high concentration to low concentration. CO2 get into the red blood cell by here. Ca is a carbonic anhydrase, get converted into the bicarbonate and hydrogen. this bicarbonate can get dissolved in the fluid, so we can dissolve it in the plasma. We don't dissolve it in the in the red blood cell because this space is limited, right? You need to dissolve that in just the water outside, right? So you will transport it out in the plasma, and then it got dissolved in the plasma. So this fluid become acidic in a way. It also has high concentration of HCO3 minus. And this blood will transport to the lung. So here is, let me go back to here. So here is that here CO2 get dissolved in the plasma, in the fluid. They will then, high concentration of this CO3 minus, it will get transported to the lung. Now in the lung is that environment has low CO2. So let's look at that in the lung here, in the lung right here, in the lung. So this one is in lung. We haven't showed that picture, but let me show here. So here is that. Now in the lung, let me move this one here. All right. Transport to the lung. So it's right here. Sorry. Yes. So that's that. All right. Transport to the lung. In the lung. Right here. Right here. All right. So that's the whole thing. Transport to the lung. When they transport to the lung, the HCO3 minus. So here you have a lot of HCO3 minus. This HCO3 minus will then the environment has low CO2. So CO2 will get moved from high concentration to low concentration. So CO2 get diffused. When these CO2 get diffused, you will also have this fluid has high HCO3 minus. This HCO3 minus will then transport back to the red blood cell, because where you have the enzyme, the red blood cell has the enzyme to convert from the H2CO3 minus. This enzyme is carbonic anhydrase. The same enzyme can catalyze the forward direction and the backward direction, so it can catalyze both directions. Then H2CO3 minus will get converted into CO2. Then CO2 get diffused out and diffused out. So in the local tissue, you convert the CO2 to bicarbonate. In the lung, you convert the HCO3 minus, the bicarbonate, to CO2, and then you breathe it out. So that's how you transport the CO2 gas from the local tissue to the lung. How? By converting it to be a solvable, like something that you can dissolve in the water. And what's it? Is bicarbonate, HCO3 minus. All right, is that good? That's it. All right, so that is how we transport O2 and the CO2. We know in the earlier video, we know that, oh, we need to transport O2. And down here, we also need to transport CO2 from here to here, right? But how, right? Now we know that O2 transport is by binding on hemoglobin. And now we know that CO2 transport is by converting CO2 to HCO3 minus. Then we can transport that. Ta-da! All right. Let me know if you have any question, okay? Let's take a break. And then next one, we are going to talk about another interesting topic in the respiratory system. That is the spirometry. So stay tuned. Be right back.